Alright, in this video we're going to look at orbital energy. Now one thing you'll notice when you look at your equation sheet is that there's this equation for gravitational potential energy that's negative gm1 m2 over r. You say, well, that's a lot different than the mgh or the mg delta y that we learned earlier. So in this video I'm going to try to explain where that comes from and how they're similar and how they're different. So if we look back to first semester and we had a ball and we elevated it in Earth's gravitational field, we said we would do work on the ball against the force of gravity, and the amount of UG gained is related to the distance, or in this term h, or delta y, that we elevated that ball. So when we do work in a gravitational field against gravity, we gain or increase gravitational potential. Now we would typically call this our zero potential line, the surface of the Earth. And so anything above the surface of the Earth elevated will gain potential energy. And for small h's, sorry, that's supposed to be an m, or delta y's, the gravitational field strength of the Earth, or the acceleration due to gravity g, remains constant, or it doesn't change enough to be negligible, or it changes so small that it's negligible. So let me write an equation here. The work done is the force exerted over the distance over which it's exerted, which in this case would be the force of gravity times the height. We know we can express the force of gravity as m times g times h. So the work done elevating something in the gravitational field will now be the universal, or the potential energy. I see the UG and I think universal gravity. The UG is the potential energy gained by that object. Now notice, what has meaning is delta UG. This is what's significant. How does it change from one point to another? The fact that we choose the zero potential to be the ground is really arbitrary. It only makes the math easier to calculate. Okay? So it's the significant quantity is change in potential from one spot to the next. All right, well now, what about looking at the same approach but for really big distances, or big r values? So on the scale of the planets or the galaxies or the solar system, what happens is that g changes as we move farther and farther away. So if I have the Earth here and I have some other mass here, as I elevate it and I do work to move it farther and farther away, the actual work I have to do decreases over time because I have to push with less and less force as the strength of gravity gets weaker and weaker. So for our equation to find the amount of work done, here we could consider g to be constant, but here we no longer can. So when we have a changing variable like that, the only way to find the total work is to use an integral to sum up over all the different radii, right? If I go from like here to here, whatever that r is, the f sub g times dr, or the sum of the work done at all those different increments. Now, you don't need to know how to do integrals in this class, but what you need to know is the only way we can solve this problem and figure out how much work we have to do is by taking an integral, because it varies, the force varies over distance as the distance varies. So what happens here, and this will be the potential energy gained, is when I take the integral of f sub g. Now f sub g we can represent as g m1 m2 over r squared dr. When I integrate this, I end up with well, the integral of 1 over r squared, these are constants, so they will pull out in front, and this becomes g m1 m2 times the integral of 1 over r squared dr. And when I integrate this with respect to r, the fact that this is r to the minus 2 makes this integral negative. So I get that the gravitational potential at some value r, between the distance between the two objects, will be negative g m1 m2 over r. And you say, well, wait, how could that be negative? Don't freak out by the negative. What matters really is that UG varies as the inverse of r, or really the negative inverse of r. So when I plot negative inverse of r, I get a graph that looks something like this. So now remember, just like over here, when we're dealing with potential energies, it's the change that's significant. It's not the overall magnitude. So I can set my zero potential wherever I want, and then it's how the potential energy changes from one point to another relative to that zero that is significant. So since this is a negative inverse shaped graph, what I'm going to do when we do universal, or I keep saying universal gravity, when I do potential energy problems on the scale of the universe, I'm going to set UG of 0 at r equals infinity. So notice, since this is a negative inverse curve, if this is my UG and this is my r, I didn't draw this really well, if I set UG of 0 at r equals infinity, then my gravitational potential is negative at all positions in space. Now, how do we use this, and how do we relate this to our little approximation here? Because this model must work, not only for things on a large scale, but also for things on a small scale. So I'm going to redraw this graph. I'm trying to get you to understand this a little better. This is r, this is UG, and this is my curve. It goes like this. Now, for really small variations, so let's say for really small changes of r's, let's just say maybe this is right here, the surface of the Earth. Let's say from here to here is radius of the Earth. So this is the surface of the Earth, and this is like, at the top of a mountain. Okay. What we see is, as I go from the surface of the Earth to the top of the mountain, my UG increases, just as we would expect it by doing work against the gravitational field. And for small approximations, this graph will appear linear, just as you would expect UG to vary linear with height as I lift something. It's only over these greater distances that you notice the changing, shifting G, therefore the nonlinear nature of this curve. So for purposes of solving for gravitational or potential energy due to gravity, on the scale of a solar system or the universe, we use the relationship derived from universal gravity, negative gmm over r. And in the next video, I'm going to show you a couple sample type problems that we can use this for modeling.